Bismillahirrahmanirrahim. So last time we developed equation of motion for a spring mass system, and we assume that the mass is at the equilibrium position, and then let's say at this instant, let's say x is the displacement, and it is in that direction. Based on that, we applied the Newton's second law of motion on the moving mass, which is mx double dot is equal to the algebraic sum of all of the forces which are acting on the mass. And when the displacement is in this direction, then the spring would stretch, it would expand, and it would pull the mass in the upward direction. So the spring force would be a pulling force, and it would be in the upward direction. So therefore, we are putting a negative sign here. Because this force, all those forces which are along the displacement, we have to take those positive, and all the forces which are opposite to the displacement, we have to take them negative. Here, so it is opposite to the displacement at that instant. So we have to take this negative. So minus kx is equal. And rearranging the equation, mx double dot plus kx is equal to 0. So we got the equation of motion for the system. But remember that in this equation of motion, x is the displacement from the equilibrium position. Sometimes the question arises in the mind that where is the weight of the mass, or what is the effect of the weight or gravity on the moving mass during the vibration. So we would be discussing this in the next slide. So actually, what actually happens when we are developing this equation? I told you that x is the displacement from the equilibrium position. So there are two positions for a vibrate system. One is the unstretched position and the other is the equilibrium position. So what do you mean by the unstretched position? Let's say I am holding this mass. I'm holding this mass such that the spring is unstretched. The spring is unstretched. So the mass is not actually supported in that case. The mass is not supported by the spring. In fact, I'm holding the mass. So the displacement in the spring would be 0, and we call it unstretched spring. And the position, let's say this is the position, the line passing through the center of the mass, and this position would be known as unstretched position. At unstretched position, the mass is not supported by the spring. The displacement or deflection in the spring would be 0. So the spring force, which is kx, the spring force is kx, k times deflection. So the deflection is 0. So the spring force in that case would be 0 because I am actually holding the mass. The spring is not supporting the mass in that case. We call that position the unstretched position. Unstretched means that the spring is unstretched. Neither it is in compression nor it is in tension. So I'm holding the mass, and then let's say I have released the mass. So what would happen? If I move the hand, so actually the gravity is acting on the mass, so that gravity would pull the mass, and the mass would move in the downward direction. But as it is connected to the spring, so it would reach the extreme position, and then it would start vibration. It would start vibration. It would start vibration about the equilibrium position, and since uh, and with the passage of time, the amplitude of vibration would decrease, and then after some time, because of the losses, the system would come to rest, and it would come to rest, and we call that the equilibrium position. The system would be in equilibrium again. We call it equilibrium position. So let's say now this is the equilibrium position. the mass is again stationary, and the displacement from the unstretched position to the equilibrium position, let's say, is delta. And we call this displacement um, static deflection. Static deflection in the spring. So delta is the static deflection in the spring. So when the system is at the equilibrium position, then the deflection in the spring is delta, and the spring force would be K delta. And in that case, the spring force would be in the upward direction. The spring has been stretched now, and it is now supporting the mass, so it would be in the upward direction. Whereas the weight of the mass is acting in the downward direction, that is mg. But the system is in at the equilibrium position. So remember that in most of the vibratory systems, when we install the system, when we mount the system, so and when the suspension in the system or the springs in the system or the elastic members in the system, they are unstretched, so they would be at that position. But once, for example, they are left over, they would slightly vibrate or move. They would move because of the gravity. The mass of the system would move because of the gravity, and the system, after some time, it would become at the equilibrium position. It would be at the equilibrium position. So remember that whenever we want to develop the equation of motion for the system, so the displacement that we would be taking, the displacement x, it would be from the equilibrium position. So this is the unstretched position, equilibrium position, and if when the system is at rest at the equilibrium position, so at this state, if we look at the free body diagram, the weight is acting in the downward direction, and the spring force due to static deflection, it is in the upward direction. And if we apply the static condition of statics, the algebraic sum of all of the forces must be equal to 0. The system is at rest, so mg is equal to k delta. So the system is not vibrating. We have not now displaced the system again, but it is at rest. It is at the equilibrium position. Mg is equal to k delta. Now the mass is supported by the spring, and the spring force is k delta, and it is acting in the upward direction. Now let's say now I'm displacing the system, and then I am leaving the system to vibrate, and then let's say at this instant the mass is moving in the downward direction and the displacement is x. Now this x is different from this. This x is the displacement with respect to equilibrium position, and this x is the displacement with respect to unstretched position. So there is difference between them. Most of the time, when we are developing the equation of motions for the vibratory system, we consider the displacement with respect to with the equilibrium position. As I discussed with you, that once the equipment or machinery is installed, because of the gravity, it would be at the equilibrium position. It would be not at the unstretched position. Once it is installed, it would be at the equilibrium position. So now again we would be applying, let's say, the Newton's second law of motion in order to develop the equation. So now we have the system is moving in this direction with displacement x. So weight is acting downward. This is the spring force due to static deflection. It is opposite to that. Let's say at that instant the mass is moving in this direction and the displacement is x. So because of this x, also there would be additional spring force, and that spring force would be kx. And if the motion is in this direction, the spring would stretch further, and it would pull the mass in the upward direction. So the spring force would be the upward direction kx. So this spring force is because of the displacement x. This spring force is because of the static deflection. Now we would use the Newton's second law of motion, that is mx double dot is equal to the algebraic sum of all of the forces which are acting on the mass. So mx double dot is equal to mg is the force which is along the displacement, so we have to take it positive. K delta is opposite to the displacement at that instant, so it would be negative, and kx is also opposite to x at that instant, so we have to also take that negative, so minus kx. So, but you know that from the static equilibrium, mg is equal to J delta. So these two would cancel each other. So mx double dot is equal to minus kx, and after rearranging, mx double dot plus kx is equal to 0. So we got the equation of motion. But remember that in this equation of motion, x is the displacement from the equilibrium position. Sometimes when you look at this equation, there is a little bit confusion in students that where is the weight, where is the gravity. So remember that weight is there, the gravity is there, but that term would cancel out in the equation of motion with the spring force due to static deflection. mg would cancel out with the spring force due to static deflection. So that term is there, but it would cancel out, and at the end, the equation of motion would be mx double dot plus a x is equal to 0. So when the system is vibrating, so normally a number of times we are talking about the initial conditions. Initial conditions, x is a function of time. When the system is vibrating, it would have displacement, it would have velocity, it would have acceleration. So x is the function of time, velocity is the function of time, and acceleration is the function of time, and they are changing with time. Time is the independent variable in that parameter, velocity, acceleration, and displacement. Initial conditions mean that when time is equal to 0, what is the displacement? When time is equal to 0, what is the velocity? So by that we mean the initial conditions. Initial condition is the time where you are starting the reading. So at that time, what is the displacement of the system? At that time, what is the velocity of the system? Let's say x and t is equal to 0. X of 0 is equal to, let's say, x naught. X dot is the velocity, and when time is equal to 0, x dot of 0 is equal to v naught. So let's say at time is equal to 0, there is some displacement x naught, and time is equal to 0, there is some velocity v naught, and we call them we call these initial conditions. So x of 0 is equal to x naught, initial displacement is equal to x naught at t is equal to 0. Initial velocity is v naught at t is equal to 0. So we have the equation of motion for the spring mass system. We have second order ordinary differential equation with constant coefficient. There is two dots, a second order ordinary differential equation because the variable x depends only on time. The independent variable is only one, which is t. So we would have the ordinary differential equation. And in the equation you could see that we are taking m constant, k constant. So it is a second order ordinary differential equation with constant coefficient. Now, if we divide the equation with m, as last time we discussed, then we would have x double dot plus k by m x is equal to 0, and k by m is actually the frequency square, omega n square. So dividing by m, and the equation in the standard form would be x double dot of t plus omega n square x of t is equal to 0, where omega n is equal to under the root k by m, which is the circular natural frequency and radians per second. So when the system is vibrating, it is moving, when the mass is moving, it would have a displacement, and that displacement is a periodic displacement, and in this case, it would be a harmonic displacement. By harmonic displacement, it means that the acceleration is directly proportional to the displacement, and it is always directed towards the mean position. X double dot is proportional to minus x. So in that case, we could model the displacement as x of t is equal to a sine omega nt plus phi. So the vibration is periodic, it is harmonic, it is sinusoidal. So sinusoidal, if the motion is sinusoidal or the signal is sinusoidal, so mathematically we could write down this as x of t is equal to a sine omega nt plus phi. A is the amplitude of the vibration. Omega n is the natural frequency at which the mass is vibrating, and phi is the phase. So if we plot that equation, that is x of t is equal to a sine omega nt plus phi, so this would be the plot. X of t is along the vertical axis, whereas time is along the horizontal axis. So this is the amplitude A, this is the amplitude A, and from here to here, it is the time period, capital T, and it is actually equal to 2 pi by omega n, and phase. Also there was in the equation there was phase. So what does that phase angle represent? So the phase angle represents the initial displacement. This is the initial displacement. Here time is equal to 0, t is equal to 0. At t is equal to 0, what is the displacement? We call that displacement the initial displacement. So this is the initial displacement. And phase, the value of phase represents the value of initial displacement when time is equal to 0. So phase determines the initial value of the sine function, and the phase is measured in radians. So meaning that if phase is 0, it means that the sine or displacement is starting from here. It is starting from here. So, but if there is phi is, if the wave is like this, then then in the model we have to include phi phase angle. So generally, when we have to take a general case, so we have to include phi in our model, displacement model. So x of t is equal to k sine omega nt plus phi. So this phi would represent what? It would determine the initial value of sine function, or in this case, the initial displacement when time is equal to 0. It would be represented by the phase in the displacement model. So again, let's say this is, let's say, a real plot of displacement. So the amplitude, you could see that the amplitude of the vibration signal or displacement is 1.5, and you could see that the signal is not starting from here. So we have to include phi if you are modeling this displacement. If you are modeling this displacement, then we have to include phi in our displacement model. So omega n is the circular natural frequency, and its unit is radians per second. Fn is the natural frequency. Fn we call natural frequency. Omega n is the circular natural frequency. And the relationship between Fn and omega n, Fn is equal to omega n by 2 pi. And the unit of Fn is hertz, the cycles per second. So once we have omega n, so we could convert that into Fn. We have to divide omega n by 2 pi, so we would have Fn in hertz. Fn is the experimental unit. It is the experimental unit. When we are measuring the frequency, we have to measure the frequency in hertz, cycles per second. Omega n is the analytical unit. When we are doing derivation or when you're doing modeling, then normally in that case we use omega n. Capital T is the time period. Time taken to complete one cycle or one vibration is the time period. And it is related, time period is the inverse of the frequency f. Capital T is equal to 1 over f, or capital T is equal to 2 pi by omega n. Its unit is second. We often speak of frequency in hertz, but we need radians per second in the arguments of the trigonometric functions, sine and cos functions. So it means normally when we do measurements or we do experiments, in experimentation, we have to measure the frequency in hertz. But when we would be doing the derivation or modeling, so in that most of the time we would be using omega n. Amplitude and phase from the initial condition. So once we have the initial condition, so we could use those initial conditions to find out the amplitude and the phase in the displacement equation. So how we could do that? We have the equation x of t is equal to a sine omega nt plus phi. So, and our initial conditions are x of 0 is equal to x naught and x dot of 0 is v naught. So I'm using the initial condition, the first initial condition in my displacement equation. So x of 0 is x naught is equal to a sine omega n and t is 0 plus phi. So from this equation I would get a sine phi. Then I have to use the second initial condition, which is x dot of x dot of 0 is equal to v naught. So for that I have to differentiate our displacement equation. So differentiating x of t is equal to a sine omega nt plus phi, we would get x dot of t is equal to a is constant, so we would get cos, the differential of sine is cos omega nt plus phi, and then when sine omega nt is differentiated, we got 1 omega n from there. So x dot of t would become omega n a cos omega nt plus phi. So if we apply or utilize our second initial condition, which is v naught of or x naught of x dot of 0 is equal to v naught, then x dot of 0 is v naught is equal to omega n a cos omega n and t is 0 plus phi. And it would become omega n a cos phi. So you would get this equation. So we have two equations, and we have two unknowns in this equation. And these two unknowns are a, the amplitude, and phi, the phase, because we want to find these two from the initial conditions. If we know the initial conditions, then how to find a and phi. So We could play with these two equations so that we could find out the capital A amplitude and the phi. So if I multiply our first equation with omega n, so I would have omega n x naught is equal to omega n a sine phi. And then I'm squaring this equation and also squaring this equation and then adding. So when I square this equation, so we would have omega n square x naught square is equal to a square sine square phi. And when I square this equation, we would have v naught square is equal to omega n square a square cos phi square. And when we add these two equations, we would have on this side we would have omega n square x naught square plus v naught square. And on this side we would have a square sine phi omega n a square cos square phi and also omega n here. So taking omega n a omega n square a square common, then in the bracket we would have sine square phi plus cos square phi. And we know that in trigonometry, sine square phi cos square phi is um, 1. That is 1. So then on this side we would have omega n square a square is equal to omega n square x naught square plus e naught square. And then we are taking under the root on both sides because we want to find a not a square and bringing the frequency terms on this side, and capital A would be equal to 1 over omega n under the root omega n square x naught square plus v naught square. So if you look at this equation, v naught is the initial velocity, x naught is the initial displacement, omega n is actually the natural frequency. So if we have the initial condition, we could find out the amplitude. And the equation for the phase, so it is very simple. We have to divide equation 2, bring that term on the other side of the equation, and then if we divide equation 1 by equation 2, then a would cancel with each other. Sin phi by cos phi would be tangent phi, and on the other side we would have omega n x naught by v naught, and then taking tangent inverse on both sides of the equation, we would have phi is equal to tan inverse omega n x naught by v naught. So again, if you look here for the phase, if you know the initial values of displacement and velocity, then we could find out the phase for the vibration. So once if the initial conditions are known or it is given or from the plot, we could find out from the displacement plot or velocity plot, we could find out these values. Then with these equations, very easy, we could find out the amplitude and phase for the vibration of the system. So displacement, this is the mathematical model for the response of the system. We call X is known as the response of the system or displacement of the system. X of t is equal to a cos omega nt plus phi. Omega nt because the system is under free vibration, a natural vibration. And if we plot this equation, and this would be the plot, we would have a sinusoidal or periodic function. Capital A is the amplitude, capital A is the amplitude. If we differentiate this equation with time, we would get the velocity. So meaning that once we have a model for the displacement, then we could find out the velocity by just differentiating that equation with respect to time. So by differentiating that with respect to time, you would get x dot is equal to cos omega nt. So differentiating it, you would get minus sine omega nt plus phi, and when it is differentiated, omega nt is differentiated, so we would get omega n. So omega n here. So minus omega n a sine omega nt plus phi. Now this is actually the mathematical model for the velocity. This is the displacement at which the mass is vibrating. So look here, this is the coefficient with the cos function, and we know that this is the amplitude of the displacement. Now look here, this is the coefficient of the coefficient with the sine function, and actually this is the amplitude of the velocity. And in order to find out the acceleration for the mass, we have to differentiate the velocity equation. So differentiating again this with respect to time, we would get x double dot is equal to a would be there, omega n would be there, sine minus is there, the sine differentiation is cos omega nt plus phi, and when it is differentiated again, you would get another omega n term, so it would become minus omega n square a cos omega nt plus phi. And here you see that the coefficient of the cos function is omega n square a, so this is the amplitude of the acceleration. The amplitude of the acceleration is omega n square a. The amplitude of the velocity is omega n a, and a is the amplitude of the displacement. So just remember that if we have a harmonic motion, and if a is the amplitude of the displacement, then we could very easily compute the amplitude of the velocity. Just multiply the amplitude of the displacement with omega n. And if you want to find out the amplitude of the acceleration, so multiply the amplitude of the displacement with the term omega n squared. If we plot this mathematical equation, so this would be this. This will be the plot. The amplitude here is omega a. And if we plot the acceleration, then you could see this would be the plot, and the amplitude of the acceleration is omega square a, or omega n square a in this case. So when the mass is moving, it would have displacement. When the mass is vibrating, it would have displacement. It would have velocity. It would have acceleration. So if we look here, this is the time, and this vertical, in this plot, the vertical represents the displacement. Look here, at when time is 0, the displacement is 0. So it means that at this instant, the mass is actually at the equilibrium position. It is at the equilibrium position. The system is vibrating, the system is moving, the mass is moving, but at that instant, it is at the equilibrium position or mean position. Then the mass, let's say the mass is moving in the upward direction, and the displacement is increasing. Here we have the maximum displacement. It means that this mass has reached the top extreme position. And then from there, again, the mass had started its journey towards the equilibrium position. And again, it would have reached the equilibrium position. Now it is moving away from the equilibrium position or mean position, and it is moving towards the other extreme position. And now here it has reached the other extreme position in the downward direction. Now again, the mass has started its journey towards the equilibrium position, and again it has reached the equilibrium position. If we look at the velocity, during vibration, the mass here is at the equilibrium position, displacement is zero. But we know that at the mean position or at the mean position or equilibrium position, the mass would have maximum velocity. So at the mean position or equilibrium position, it has a maximum velocity. As it is moving towards the extreme position, top extreme position, its velocity is decreasing. And its velocity would become zero because at the extreme position, the mass would become stagnant. So its velocity would be zero. Then again, it would start moving, the mass would start moving towards the equilibrium position. So the velocity would again increase. And when the mass reaches the mean position or equilibrium position, its velocity would be maximum. And again, as it starts moving towards the other extreme position, its velocity would slowly and gradually decrease, and it would reach the other extreme position. Its velocity would be, become zero, and then again its velocity would start increasing. And as it reaches the equilibrium position, its velocity will be maximum. If we look at the plot of the acceleration, when the system is at the equilibrium position, displacement is zero, the acceleration is zero. And as the mass is moving towards the uh, top extreme position, as it reaches the top extreme position, the acceleration would be maximum, negative direction. Deceleration, in other words, the deceleration will be maximum. And similarly, as it starts moving towards the equilibrium position from the extreme position, and as it reaches the mean position or equilibrium position, again its acceleration will become zero. And as it starts moving towards the other extreme position, the acceleration would increase, and at the other extreme position it would be maximum, and so on. Remember, if you look at these plots, if you look at these plots, you could see that this is the displacement and this is the acceleration. The acceleration is out of phase. The acceleration is out of phase to displacement. There is 180-degree phase angle between the displacement and acceleration. The acceleration peak is on the top side, here the acceleration peak is at the negative side. So it means that the displacement and acceleration, they are at 180 degree or out of phase. Out of phase, they are out of phase. And you could also see the phase between the velocity, phase angle between the velocity and displacement. So if we plot the angle between these omega t is theta, and let's say this is the displacement vector, then the phase angle between the displacement and the velocity is 90 degrees. And the phase angle between the displacement and acceleration is 180 degrees, is 180 degrees. Note that the velocity leads the displacement by 90 degrees, and the acceleration leads the velocity by another 90 degrees, or the acceleration is leading the displacement by 180 degrees. So remember this in your head that they are not in phase. There is a phase angle. The velocity is leading the displacement by 90 degrees, and the acceleration is leading the velocity by 90 degrees, or the acceleration is leading the displacement by 180 degrees. So you have to also include those in your mathematical model. So we have a spring mass system. This is the equation of motion for the spring mass system where x is the displacement from the equilibrium position of the system. And the response of the system, which is x, if the vibration is harmonic, then the mathematical model for the response or displacement is x of t is equal to a sine omega n t plus phi. The other form of this response is actually the solution of this ordinary differential equation. In mathematics, this is the solution. In vibration, this is the displacement or response of the system. The other form that actually satisfies this second order ordinary differential equation with constant coefficients that you may have studied in mathematics are x of t is equal to a 1 sine omega nt plus a 2 cos omega nt. Because the sine function is actually the solution of this differential equation. Similarly, the cos function is actually the solution of this differential equation. And you have studied in mathematics, if we have two solutions, if A is the solution, B is the solution, then the sum of these two would also be the solution of the differential equation. So the sum of these two, that is the sine function and cos function, would also be the solution of this differential equation. But remember that in this equation, A1 and A2 are not the amplitudes. Here, A is the amplitude of the response. Here, A1 and A2 are not the amplitude of the response. They are arbitrary constants. And in order to find these arbitrary constants, we have to use the initial condition. Similarly, we could model this response or displacement on the complex in complex numbers. So x of t is equal to a1 exponential j or I omega nt plus a2 exponential minus j omega nt, where a1 and a2 are the arbitrary constants. And in order to find these arbitrary constants, we have to use the initial condition. So these are the other forms. One could use this equation for the response of the system during modeling. We could also use this mathematical model for the response. One could also use this depending upon the convenience of the specific problem. Sometimes we assume this as the solution, sometimes we assume this as the solution, and sometimes we assume this as the solution, depending upon the convenience or easiness by which we could solve our problem. So actually this is the response on complex numbers. So x of t is equal to a1 exponential omega n jt plus a2 exponential minus omega n jt. So how this is response? We have the equation of motion for the system, and let's treat this as in order to find out the solution, we are using the eigenvalue problem. We are assuming that x of t is equal to a exponential lambda t. When we are doing that assumption, we are making the eigenvalue technique or eigenvalue method to solve the differential equation, or in order to find its solution. So let's say this is the solution of this differential equation. If this is the solution, it must have satisfied this equation. So here we have x double dot. So x dot of t would be equal to a exponential lambda t, and when it is the differential of exponential lambda t is again exponential lambda t, and when we differentiate the power, we would get a lambda exponential lambda t. And when we again differentiate this with respect to time in order to have x double dot, then we would have x double dot of t is equal to a exponential lambda t, and then when again it is differentiated, again lambda would come out, and then we would have a lambda square exponential lambda t. So putting for x, a is here, so x is a exponential lambda t, and putting for x double dot, and is already there, x double dot is lambda square a exponential lambda t. Now we could take a exponential lambda t as common. So inside the parentheses, we would have m lambda square plus a equal to 0. So here out of the parentheses, we have a exponential lambda t. So we have the product of two equations and it is equal to 0. It means that either a exponential lambda t is equal to 0, or everything which is inside the parentheses, it is equal to 0 during the vibration. We know that a exponential lambda t is the displacement, and during all of the vibration, during whole of the vibration, the displacement is only, we know that the displacement is 0 only at the equilibrium position, but at all other intermediate positions and extreme positions, the displacement has values. So during whole vibration, at all instances, mean that a exponential lambda t could not be equal to 0. It means that m lambda square plus k is equal to 0 at all instances during the vibration. And this equation is known as the characteristic equation of this differential equation. So the characteristic equation of this differential equation is m lambda square plus k is equal to 0. So what we have done, we have used the eigenvalue method, and we have converted a ordinary differential equation into an algebraic equation. So now it is very easy. We know that it is very easy to solve the algebraic equation. So we would just use the quadratic formula to find out the roots of this algebraic equation. It is a second order algebraic equation. So using the quadratic formula, lambda is equal to plus minus under the root minus kn. The quadratic formula you already know, so utilizing that quadratic formula, which is I think plus minus and negative sign. So here negative sign is there. So under root minus 1, we could take this as iota or j. So now lambda would be plus minus under the root j or iota k by m. Or lambda is equal to plus minus k by m under the root is omega n, so plus minus omega n j. So we have two roots for the characteristic equation. One is with the positive and other is with the negative. So x of t is equal to a1 exponential, that is with the positive lambda, exponential omega n jt, and x of t with the other root, which is equal to a2 exponential minus omega n jt. So this is the solution of that differential equation, and also this is the solution of that differential equation. Both are the solutions. So the sum of these two would be also the solution of this differential equation. So x of t is equal to a1 exponential omega n dt plus a2 exponential minus omega n dt would be also the solution of this differential equation. And this would be also the response of this differential equation. So we could represent the response of the system also in complex numbers. So we could use any model depending upon our convenience. Sometimes we use this model for the response of the system. Sometimes we use the other model, that is the sum of sine function and cos function, and sometimes we would use this model. But remember, if you look at the equation, in this equation, A, there are two unknowns, A and phi. Also in this equation, there are two unknowns, A1 and A2. And also in this equation, we have two unknowns, A1, small a1 and small a2. So all these equations has two unknowns. Once we have known these two unknowns, we know the values of these two unknowns, then in that case, we actually completely know the response of the system or displacement of the system. And in order to find these two unknowns, normally we are using the initial conditions.